So let's get started. Welcome. Lecture number 7. We're above the mean now and the median also. So welcome to this. Maybe, yeah, you're right. Mean, median, whatever. Now, I don't know how many series you follow on Netflix or other places. Personally, I find my life has much too few hours to be able to follow all those that you think you should. But hey, why follow series on Netflix if you live one in real life, right? So here is another breathtaking episode that not alone will bring you enjoyment and entertainment, it's also thought-provoking and moves you in life. Give me one Netflix series that can give you that each episode, and I'll watch it. Here we are. Today we're gonna go as far as this guy. He doesn't look real, but there was a guy with that name actually, and we will learn why. He is a pretty magic guy. If you had my age, the stories were still told and read back then. Today, I don't think it's that common. But anyway, we're going to do a brand new thing today. We're going to do statistics by using the computer to simulate the stuff for us. Instead of using the t-distribution and the chi-square distribution to do statistics, to do the confidence intervals, I'll let the computer do it for me. This is the brand new thing today. As part of that, we have this plan. It's roughly split here, in spite of the many titles below the line there. We're going to talk about simulation as a probability calculus tool and the way we can use that to do statistics. And in doing that, we're going to learn the concept of bootstrapping. That's where Baron von Münchhausen gets into the picture. It's magic, and it works. What is simulation really? Well, it's a little guy inside the computer who throws the dice for us, right? And tells us some random numbers. Well, why should we think about this in our statistics class? That we can have the computer do random experiments for us. Because many of the things, and I'm actually maybe even speculating, maybe most of the things, most of the real life challenges that will hit us as engineers in our future will, when we want to be intelligent about looking at the numbers, that is, we want to know about the sampling distribution. I taught you that's the statistical words for try to think about what the number can really do for you. And that's what's the sampling distribution of this number? How could it change from time to time? Many of those features out there in the world waiting for you do not follow the t-distribution nor the chi-square distribution. Now this is a good start with the t and the chi-square. T for the mean, chi-square for a variance. Hey, engineers do not live just from simple means and very simple variances. We need to get moving from that point. There could be other things that we might want to compute. All sorts of things that we may just mention or not even touched in this course. There's something called a trimmed mean. That's kind of a robust mean, where you throw away the most extreme observations and just use the middle 90%, for instance. We did meet the median. We did talk about quantiles. I have not given you any statistical tools for looking at medians or quantiles. The median story might be a little with the log normal. We have a little thing there. But generally, I didn't do, then let me take the next one, coefficient of variation. That was the standard deviation relative to the mean, for instance. That's also a feature. Interesting. You compute it very often. What's the statistics for that feature? How do I do the confidence interval? What about hypothesis testing if you want? Today we focus on confidence intervals. That's the most intelligent thing. Well, I didn't give you the tools. Why didn't I give you the tools? Because they are mathematically complicated. So in the old days, you didn't do it because it was not easy. It's not a t-distribution, it's not a chi-square. We cannot do it. What about actually any kind of nonlinear transformation of the stuff that we're computing? There are many systems, dynamical systems whatsoever, controlling windmills or dynamical energy control in a house or whatever, that are complicated nonlinear systems. And we compute something and we do complicated nonlinear transformations of what we compute, and we always have to do the question, how good is this number? What's the sampling distribution? What's the uncertainty? Can I really use it? Well, it's a nonlinear transformation. No one taught me that. Why didn't we teach you that? Because it's mathematically complicated. But after today, it's not an issue. You have the tool to do it. That was one motivation for going on from what I've taught you so far. Another motivation is not every phenomenon that you will meet is a normal distribution in the outset. Then we had the CLT, that we could hope for the magic of CLT, and I was pretty enthusiastic on the day that I talked about the CLT. The CLT is pretty magic, but it doesn't solve everything everywhere always for us. And the problem, if we are really pushed at the wall, we have difficulty in making the decision whether the CLT is good enough or not. And you're not going to be saved by the rule of thumb n equals 30 if you go to a courtroom in the US. It's not good enough in a courtroom that some statistics teacher told you, well, n equals 30, I could always use the CLT. This is not how simple life is. You have to be more intelligent. You have to investigate that yourself. We can do that by simulation. And we can use R or any other software for doing that. In this course, we use R, pretty nice tool. So what is it really? When we do simulations, random simulation in the computer, we generate random numbers. And this is the little man inside the computer throwing the dice for us. Now the little man, right, there is no little man in the computer, right? It's actually just a computer. What the computer can do for us, the computer can take one number, xi, and then through some algorithm, mathematical formula, it can generate the next one, and the next one, and the next one, and the next one. And it can do it in such a way that when we look at this long list of numbers and look at how it distributes itself, we cannot distinguish these numbers from real random numbers. And the place we usually start is that random uniform numbers between 0 and 1 is what the computer is in the outset going to do for us. So random number generators are algorithms that produce such sequences that are random numbers between 0 and 1. Some decades ago, it was a big issue, research about what are the best random number generators, but this is all basically settled. All our nice fancy software have really good random number generators, R, Python, Excel, you name it. Everyone is pretty nice. So that's not a practical problem, that all works nice. The way it actually works in the computer, then, it needs to start somewhere. Like I say, if you give it a number, it can continue. That's the thing. So it needs to start somewhere. Sometimes we control that. You'll see that in R. You can control it. It's called a seed. If I want to be able to, for you to be able to reproduce exactly what I show you, then I use the seed. For the usual work, we don't really need the seed, and if you use it too much, you can run into problems, actually. But anyway, you can control it. If you don't tell the computer where to start, it looks in the clock and finds some number where it uses some clock number to start, right? So it finds a number, and then it goes from there by itself. So you don't need to seed it, but you can do it. Now, there is one mathematical result here, which is, well, I should not oversell it. You don't really need it. You couldn't care less because the computer does it for you. But this is one of those results that are so basic and so nice that it would almost be a criminal offense not to share it with you. Here it is. you have something which follows a uniform distribution. That is, if you can generate random uniform numbers, you can generate anything. Because you can take the inverse of some distribution function, and the inverse applied to the random numbers produces numbers that follows that distribution. Can you see the scope of this theorem? Give me any f of any kind of distribution, I can use the uniform U to generate observations from that distribution. We have this little picture here of the exponential distribution. Let's go and do it actually. I think we can come back to our friend here later. Here. Let me skip the seed here because I want to do something new each time. And then I need to go like this. I need to do like this for everyone to be able to see. And now I do something here. What I plotted here, the function, that's the distribution function for that exponential distribution, right? That's the accumulated probability function. And then I show you how, if I generate numbers, and that's actually what I do here, I generate 5 random uniform numbers, R-unif, that produces 5 numbers between 0 and 1. And then what I do is to actually take it through the inverse of that distribution function. So I go backwards. These numbers down here, they come out as exponentially distributed numbers, right? So again, you couldn't care less maybe, because there is a much easier way to do it in R, because R also has a random exponential function. But you could do it like this. You could, using the theorem, randomize uniform numbers and then take it through the quantile, which is the inverse probability distribution function of the exponential. That would produce exactly the similar type of numbers. And in fact, that function you could also extract analytically. Here's the inverse distribution function extracted analytically. So that's just to give you a hint of the basics here of what the computer can do for us. Because then here's the name of the game for you, right, really, that they are all there. We already met quite a few of them previously in the course. We can look at the R, if you didn't realize that before. R, right? You can randomly do sampling from any of those distributions. That's pretty neat. Let's start the game, if you still want to play. Do you need a bit of mood to get started? I don't know why I'm even reading those names, but what should I do else standing just waiting here than reading your stupid names? But then again, I need some input for a speech I'm going to give, so maybe I should have a look at, get inspired. Are we there? I think we are. Are you ready? Right? This is the uniforms. And then we go back with a normal with a mean of 4 and a standard deviation of 2, which is the same as a variance of 4. We have the old dancer there. That's good to see. If the dancer wins, I'm going to do the dance again. So let's hope not. Oh.